Okay, so this is problem 1315 that's on page 562. The two blocks shown start from rest, and it is observed that the velocity of block A is 5 feet per second after it has moved through 6 feet. Assuming the pulleys are massless and frictionless, determine the coefficient of kinetic friction between block A and the incline. All right, so what do we have? We have a mess. This is problem 1315. We've got an incline, 200-pound block moving up the incline. And let's see, cable, which ultimately is attached to the ceiling. Another pulley attached to a block that is a 300-pound block at B. This one's at A. And the angle is a 30-degree angle. Now, what makes this problem more difficult or different than problem 13 is that there is friction between block A and the incline. So there's some coefficient of friction. We don't know what it is. We're supposed to find it. Now, this is also a little more tricky than the last problem, which was essentially chapter 12, problem 18 all over again, but with energy. This is more difficult because the velocity of block A and block B are not equal. Now, it's pretty easy to see the relationship between the velocity of the two. Anyone want to hazard a guess before we write down a rope equation and figure it out? What's the relationship between the velocity of block A and the velocity of block B? Neglecting the direction.
It'll be twice what these.
2 to 1, right? Okay, so which one's going to move faster, A or B?
A.
A, right? Because if you get B to move down by 1 foot, well, that's 2 more feet of rope, 1 foot on each side. And so block A has to move up 2 feet. Okay, so that's the easy way to think about it. We could write down a rope equation, but it looks like you guys have the gist of it, so we won't bother. I would suggest you try a rope equation with this. Oh, I guess this wouldn't quite work yet, would it? There's the other thing. I would suggest you guys try to create a rope equation for this just for practice, because what's interesting about this is that the reference point for the motion of block B has to be here, whereas the reference point for block A should be over here. So you got to figure out how that works, because block A is moving in a different direction than block B. Anyway, what do we know? What are we given? Well, we're told that the velocity of A is 5 feet per second after it has moved through 6 feet. So delta XA equals 6 feet. Okay, and that's all we're given. So what do we usually start with in chapter 13? Well, for chapter 12, it's a free body diagram, but for this one, we usually start with a conservation of energy equation. Okay, so let's just write that down. You're right. I mean, there's nothing wrong with a free body diagram, because you've got to figure out what forces are acting and how those forces act in order to solve the problem, right? In fact, we've got this internal tension in here, and we have to be kind of careful, because the force, the tension over here, acts through a different distance than it acts through over here. Now, do you guys think the tension will still cancel out or no? Well, think on it for a minute, we'll figure it out. Let's start off with our energy balance and say that the kinetic energy in state 1 plus the work done in going from state 1 to state 2, which is from still to moving at 5 feet per second, is equal to the kinetic energy of state 2. Let's figure out what all should go into these. And it sounds like it starts from rest, so neither block A or block B have kinetic energy initially. Just like the last problem, the initial kinetic energy goes away. How about the final kinetic energy? Well, that's not too bad, right? Because we've got the velocity of A at the final state. You just told me that the velocity of B would be half of that, right? So the right-hand side's pretty much done. If we were to expand it to a 1/2 mass of A, VA squared plus 1/2 mass of B, VB squared, you could plug numbers into this and you'd be done. The right-hand side's a number now, right? Because we know the masses, we know the velocities. In fact, let's just go ahead and note that this suggests the velocity of B is 2.5 feet per second, so that's out of the way. So the right-hand side's easy. How about the left-hand side? Well, on the left-hand side, we've got to make a couple of decisions. We have to decide if we should include the tension in the ropes or not. Obviously, we have to include gravity, and is there anything else we have to include? There's friction, right? And that friction is a force that's going to act through a distance, because that friction acts in what direction? Up the incline or down? It acts down. So is it going to be positive or negative on the left-hand side? In other words, is it going to give us kinetic energy, or is it going to take away from the kinetic energy? It'll be negative, that's right. So the term for the friction, the work of the friction on the left-hand side should be negative. Why? Because the friction's in this way, the motion's in this way, right? Even if block A was sliding down the incline, then the friction would be this way and the motion would be that way. Friction will always be a force that removes energy from the system. So you should always have a negative sign in this equation on the left-hand side if it's a frictional force. Does that make sense? Okay. So let's enumerate them. And in fact, bless you, I think your idea of a free body diagram is a good one. So let's do it down here. Free body diagram. Block A, we've got a tension force acting up the ramp, a friction force acting down, a weight force acting directly down, not down the incline, and we also have a normal force. Which one of these forces does zero work on block A? There's one. Which one is it? The normal force, that's right, because the direction of motion is perpendicular to the normal. So while it's still there, it still exists, we don't need to consider it. So the normal force just goes away as far as we're concerned. Notice the frictional force is the unknown, so don't worry about trying to multiply the weight by the frictional force or by the, let me back up. Don't worry about trying to multiply the normal force by the coefficient of friction at this point. We're not worried about it yet. Okay, we'll figure that out later. We just need to figure out the magnitude of the friction force, and then we'll figure all that out later to come up with the coefficient of friction. Okay, so there's the free body diagram for A. How about for B? Well, let's see. B has, I'm going to attach the pulley to it so I can show you that there are two tension forces acting on B, as well as the weight force of B. Let's differentiate that from the weight force of A.
Not just be one, since the pulley is only in contact with the block in one spot.
Would this be 1? It would be 2T at this point.
Well, I meant, all right. I was just wording it in a different way, but you can reference it by 2 or 1 symbol.
Right, right. I use this symbol so that these tensions would be the same as this tension. That's why I did it this way. Otherwise, if I did it this way, I would get the idea that this is 2T from a free body diagram of the pulley itself that's right here, right? We've got T here, T here. Since this is massless, this has to be 2T. Okay. So either way is fine. Okay, so I'll leave it that way. Now let me ask you another question. Does that mean that the tension is just half the weight of B?
No, there's acceleration.
That's right, there's acceleration. And so these two must be imbalanced because we know there's acceleration. So don't just go back to statics and think, well, no big deal, the tension is just half the weight of B. Okay. So basically, the effect of all these forces have to be included. Now, if we look at this, let's see. Let's start off with weight, because weight's an easy one. So negative weight A delta Y of A, negative weight B delta Y of B. So that takes care of gravity. Now, we need to decide, are we going to include these tensions or no? They are internal to the system. Well, think about it for a minute. The force being applied to block B is twice the force being applied to block 1. But the direction of block B is downward and only moves half the distance of the distance of block A, right? Block A is moving up the incline, so the force multiplied by distance is a positive thing. It would essentially be T times some distance. Let me call the distance that block A moves. Well, in fact, it's already here. It's delta XA. And what this tells us is that delta XB, which really would be in the Y direction, unfortunately, okay, because it's going to be block B moves up and down, is just going to be 3 feet. Right? In other words, block B, as you know, will just move down 3 feet. So 3 feet multiplied by 2T is going to be the same thing as 6 feet multiplied by T. So once again, the internal forces are going to cancel out, and we don't even need to consider the work that the tension does on the two, which actually makes sense. A lot of students get confused because they see the tension acting up here in this rope, and they feel like, well, maybe that tension actually does some work on the system, and they get into the idea that we could maybe build a free energy device because of this force. Well, actually, that force doesn't act through a distance up here. It does act through a distance down here, because this is the point that moves, not that point. Anyway, the point of all this is that we don't need to include the tension at all. We know that these would cancel out just by inspection. Okay? We've already taken care of the effect of the weight force. We haven't really calculated it yet, but we've at least got it in the equation. And then what? Well, then we've got this term, which is going to be simply negative F delta X A, right? Why is it negative? Because delta X A is positive. F multiplied by it should give us something negative, something that is taking away from the kinetic energy that there could be. Does that make sense? In other words, another way of looking at this, the work done by gravity has to supply the kinetic energy and overcome friction. Okay? You could really move this to the right-hand side of the equation if you wanted to. It would make a lot of sense. Now, the thing that we're looking for is this frictional force F. So instead of moving this to the other side, let's move everything else to the other side. So the frictional force times delta XA, and actually I guess I misspoke. What I'm going to do is move this term to this side, move everything else to the left-hand side. So negative weight A, delta YA, negative weight B, delta YB. Let's see, I'm going to run off the board here, so I have to say, let's see, this all needs a negative sign on the other side, so minus 1/2 mass of A, velocity of A squared, plus mass of B, velocity of B squared. So if we just divide this side by delta XA, then all we have on the left-hand side is the frictional force, and we should be closer to solving the problem. All I did is I divided this out. If you're wondering what happened here, I had to break the line again because I ran out of space. Okay. Well, I claimed that we could just make this a number, so let's do it. Let's start off with, let's see, how do I want to do this? I think I'm done with the free body diagram, so let me get rid of those. I'll move the delta XA information up here. 6 feet, delta XB is 3 feet. Let me try that again. That's something you can't read. Delta XB, 3 feet. That'll take care of these two. And you know what? We've got the velocities right here, so we may as well go ahead and calculate the second term. So, sorry?
You drop a negative
Did I drop a negative? I moved this term to the other side,
oh, okay.
which is why these remain negative, and I moved this term to the other side, which is where that negative came from. Good question. I could have moved these over and then divided by negative delta XA, but it doesn't matter. So negative 1/2, I need the mass of A. Well, the mass of A is 200 pounds mass. Let's see, I'll have to go ahead and use pounds mass because I can't just add the weight of B. I need the velocity of A squared, so that's 5 feet per second, quantity squared. I need a more precise marker. I think this one's pretty wide. Okay, I need the mass of B, 300 pounds mass, times the velocity of B, which we decided would be 2.5 feet per second. All that has to be squared, and that ends the term. So now I need some calculator help, please. 5 times 5 is 25. So 25 times 200. I don't know. I could do it in my head, but I don't feel like messing with this. I don't feel like squaring 2.5 in my head. I could. It's easy. It's what,
6.25.
6.25? 6.25 squared?
Yep.
That makes sense. Okay. See, I would have gotten that one wrong. That for calculators. So what number do we have here? I need calculator help.
You didn't include the weight A?
Not done yet. Just working on this piece.
Okay, okay.
Yep. Okay. Let's see, should we go ahead and convert this? We're going to need a frictional force in pounds force. So why don't we go ahead and convert? Let's see, there's 1 pound force per 1 pound mass, 32.2 feet per second squared. So we'll just go ahead and take the result and divide by 32.2. And I got a force of negative 106.75 or so pounds force. Everyone agree with that? Did I do something wrong? By the way, I do suggest you bring your calculator and go through this. I've had students tell me in the past they like this because it keeps them engaged and makes them think. Plus it gives you practice working equations and plugging into things like you'd have to do it on the exam. If you're going to see equations like this on the exam, you may as well get used to working it on your calculator. This is good practice. So I do suggest you bring your book and your calculator to class. Did I mess up or is that okay? All right, so we've got a couple people saying it's all right. Okay, then let's continue. So we've taken care of this piece, and let's just make a note over here of what it is. It's negative 106.75 pounds force. Now let's use the space again to calculate the other term. And we can just take the ratio of those two terms, divide it by the distance, and we should be okay. We need negative weight A delta YA less weight B delta YB. Delta YB is pretty easy, right? Delta YB is negative 3 feet. Right? Now why is it negative? Because, be careful, this always includes a sign. It assumes that the positive direction is opposite of gravity. And that's why this negative sign is here. So the second piece is pretty easy. The weight of B is 300 pounds force, because 300 pounds mass would weigh 300 pounds force, okay, on Earth, multiplied by delta YB, but delta YB is going to be a negative 3 feet. So another way of looking at this is that block B dropping is supplying the kinetic energy, the frictional energy, and since block A is rising, it's also supplying the potential energy for block A as well as the friction for block A.
How delta YE negative do you think?
Why is this negative?
Yeah.
Because block B moves down in the gravity field.
Okay.
And we always take our positive y direction to be opposite of gravity for the sake of this piece. Okay? Good question. Please do ask questions if you have anything else. All right. Now this part's not too bad, but it may be a little bit confusing at first. The weight of A is easy. That's 200 pounds force. But what about delta y of A? Well, delta y has to be a dimension in this direction. So what we're really interested in is not 6 feet, but how far up. This is, well, I don't have room for it there. Let's try it here. Delta y A is right here. It's this distance. This distance is delta x of A, right? That's the 6 feet. So how do we come up with this height? Let's extract the triangle and look at it. So we've got a 6-foot height on this side. We're interested in delta YA. We've got a 30-degree angle over here. So what's the relationship? Sine or cosine?
Sine.
Sine, that's right. So this would be equal to 6 times the sine of 30 degrees. If you plug that in your calculator, I'm pretty sure that's half, right? So this is 3. Yeah. So that makes it easy. So delta Y of A, is it positive or negative?
Positive.
Positive, because it moves up the gravity field. That's right. So this is 3 feet. Everybody see that? So what's the net effect? Well, we've got negative 600 plus 900, which is 300. So there's 300 pounds force feet available for supplying friction and kinetic energy. Notice we've already taken into account raising block A. Right? This is what excess is available for the friction and the kinetic energy. Okay. All right. So now let's go over to our equation here and say that the frictional force F must be equal to, we have 300 pounds pounds force feet for the numerator. Let's see, minus, wait a second, I've got a problem here. I wasn't careful with my units. I just had negative 106.75 pounds force. It should have been pounds force feet. Let's check the units and make sure that it came out. Do you remember the mass was in pounds mass? The speed was feet per second, but that was squared. And then I multiplied by G sub C, which had units, and I'm just going to write down the units now, not the numbers. It had units of pounds force per pound mass per foot per second squared. Okay? So the pound mass went away, we had pounds force, and I forgot that the seconds would go away, but one of the feet would remain. Do you see what happened? Yes?
Now, I feel like I'm kind of wrong numbers. I thought that you always took pounds mass times the acceleration of gravity.
You do. What I'm doing here, that's why I said I'm just looking at the units. The numbers, I've already figured out the number,
Yeah,
but I missed the feet before.
we divided by 32.
That's correct. Once again, I'm neglecting the numbers here. All I care about is the units.
Yeah.
These are the
No, I
units.
was wondering why, I know it's already been erased, but I was just wondering why we divided by 32.2 instead of multiplying by it, because I thought it was pounds mass times 32.2.
Are you saying you wanted me to write this?
Yeah, I'm wondering why we divided by 32.2 instead of that. I always thought that pounds
Before we
mass
multiplied.
times,
When we were doing this before?
yeah.
Okay. The reason is because a pound mass times a foot per second squared is a unit of force. A pound mass is not a unit of force, it's a unit of mass. Okay? A pound force is a unit of force. A pound's mass is a unit of mass, but a pound mass foot per second squared is a force. Okay, does that make sense now? No, it's okay, please. If there's more, please ask.
It just feels like I've been thinking it the wrong way the whole time.
You probably have been. That's probably why G sub C is so confusing to most students. G sub C is just a conversion factor. And I wish that when it was taught that they would just say, look, here's some units of force. They're pounds, mass, feet per second squared. Those together are a unit of force. Just like a foot per second squared is a unit of acceleration, right? A foot is a unit of length, a second is a unit of time, but a foot per second squared is a unit of acceleration. Just like a pound mass foot per second squared is a unit of force.
All right, sorry.
No, you're fine. This is good.
Finally looking at the units, it makes sense now.
Okay, good, good.
I
It
was
clicked
thinking
for you.
straight pounds mass, pounds force, not pounds mass, like you're saying. So
Yep, good, good. That's why I teach. I enjoy I like seeing the light come on. The students go, oh, I get it now. You know, it makes sense. And don't worry about it. I mean, you know, the fact is we're fortunate to stand on the shoulders of giants. You know, I would have never figured out anything of what I've learned in my whole lifetime. I'm just glad I had the opportunity to learn it, you know. So these are good questions. I think I saw another hand earlier. You all right? Okay. All right, so I just forgot to check my units, and hopefully you don't forget to check your units. So fortunately I had units on this piece, and so when I tried to add just pounds force to it, I realized I'd missed something. So less 106.75 gives us the whole numerator, and we need to divide by delta XA. Well, delta XA is 6 feet. And why is it 6 feet and not the 3-foot elevation height? Because the friction acts over 6 feet. The friction acts up the entire incline. It doesn't care that the block's only moving up in the gravity field by 3 feet.
So is the frame of reference tilted?
Is the frame of reference what?
Tilted at a 30-degree angle?
Good question. Is the frame of reference tilted? I haven't really drawn a coordinate system here. I'm just talking about distances moved through, or yeah, that a force is applied.
Well, because if we're talking delta x, wouldn't it be 6 cosine of 30?
Here's what you're getting at. We usually use a coordinate system like this. X to the right, Y up, or sometimes we'll tilt it when we have an incline like this. I've always said this course is kind of like physics on steroids, because a lot of these little things we just start taking for granted. And so in this case, this delta x, I'm talking about this coordinate system. When I'm talking about the delta x of b, I'm talking about a coordinate system like this, but I'm relating it back to this delta x of a, so I called it a delta x, but really it's a delta y. Are you confused yet?
No, I get that. I just don't understand why we took delta y of a.
Okay. Why do we take delta y of a as this instead of this? Because we're interested in the distance along the same direction as the force. So when we took delta ya, we were interested in what gravity was doing, and gravity acts in this vertical direction. When we took delta x of A, we were interested in what friction was doing, and so we took it in this direction.
So
Good question.
in that context, it's tilted.
Right.
And B, it's
Exactly.
vertical.
Good job. Good question. Anything else? Okay. All right, now what? Well, let's see. We've got some numbers here. The feet will go away. I forgot my units here too, but they'd run off the video, so I'll put them here. And we'll just have pounds force for our friction force, so that's a good thing. Let's see. I still have the answer with all the decimal places, so I'm going to use it. So if you get a slightly different number, because I haven't rounded this number off. So let's see. Putting all that together, dividing by 6 feet, I get that the friction force is 32.2 pounds force. Okay. So there we go. So there's our, now I did round that off, it's slightly different. So there's our frictional force. But that wasn't really the question. The question was, what is the coefficient of friction? Well, the coefficient of friction is going to be equal to the normal force. Let's write it in the order that I'm saying. The coefficient of friction will be equal to the, I can't speak. My brain is going too fast and my mouth can't keep up. The frictional force will be equal to the coefficient of friction multiplied by the normal force. There we go. So all we really need now is the normal force. Could we figure out the normal force? Well, sure. The normal force, remember we had our free body diagram, and we said the normal force would act up this way, the weight would act down this way. The only component of the weight that did any work was this component. We took care of that by using delta y with the weight of A. But the normal force would be this other component, right? Because we know the block does not accelerate in a direction perpendicular to the plane, right? And so this component of the weight, make it look right, is what we need. So how would we get that? Well, once again, I suggest you extract a triangle and figure it out. Let's see, the weight would be the hypotenuse. So there it is. This line is perpendicular to this line. Okay. So let's see, let me add some lines on here. So those two are perpendicular. And then this line is perpendicular to this line. So what does that tell you? Well, the angle between these two you know already is 30 degrees. And since it's mutually perpendicular to these two lines, then there is our 30-degree angle. Okay? Sorry it's so small. Hopefully you can see that. So basically what I'm saying is that this is a 30-degree angle. And so to get this component over here, which is what I want, this piece here, do I need to use sine or cosine? Cosine, good job. So I need the weight multiplied by the cosine of 30 degrees, and this is the weight of A, by the way. So let's see, let's figure that out. The weight of A is 200 pounds force, cosine 30 degrees. This is the one that's not quite as easy. It's 0.866 something, I think. So let's take cosine of 30 multiplied by 200. And you get 173.2 or so pounds force. That's the magnitude of the normal force. And really what we want is the friction coefficient. So we have to take the frictional force divided by the normal force. That should give us our number. Okay. So I'm going to invert what I've got in my calculator to represent 1 over n and multiply it by f, which is 32.2. And I get the friction coefficient is about 0.186 or so. And it's dimensionless, of course, because it's a ratio of two forces. 12 pounds force. Okay? Any questions?
So the normal force would be 173.2, right?
Correct?
Where do you get that number again? It's like...
It's the weight times cosine of theta.
Oh, okay. I thought, yeah.
Sorry, I'm moving around a lot on the board. Anything else? All right.